Let's talk a little bit now about some of the landforms that glaciers can leave behind. Mostly this refers to things that we can see on Earth's surface after the glaciers have receded and disappeared, and we can look at those landforms as evidence that glaciers used to be in certain locations. When we talk about glacial landforms, it does include some characteristics of glaciers themselves. If you were to go and see a glacier, you would see things called crevasses that are actually in the ice. But for the most part, it really refers to those landforms left behind after the glacier recedes. Because for the most part, we're not interacting with the glaciers as much as we are interacting with those landforms left behind by glaciers, which used to cover much more of Earth's surface than they do now. And that happened in the recent past 20,000 years or so. You will want to know what each one of these landforms is or looks like and how each one forms in, sort of a one sentence sort of description. We'll start with the one feature that we can see on glaciers themselves, which is called a crevasse. Those are cracks in the ice surface itself that forms because that glacier is flowing downslope. So they form where the glacier moves over a change in underlying topography, right? So you can imagine as this glacier is flowing this way over this break in the hill slope, that it will start to fan out a little bit and you'll form these cracks along the surface. They also form where the glacier has to move around curved topography, right? So wherever the glacier is changing direction on the topography below it, you have crevasses forming. Let's take a look at an example of one. Here I've pulled up our Google Earth of Mount Rainier in Washington State. And if I tilt this, you can see this is a pretty tall snow-capped mountain. And it has several glaciers running down it in these mountain glacial valleys. So there's one over here, right? So over, right now it's dragging. Okay, so you see one over here, I'm indicating with my cursor, one to the south, a couple to the south actually. And on a lot of these, you can see those crevasses that I was talking about, those cracks in the surface. We can tilt it, we can try to zoom in on some of these to get a better look. But you can see that these crevasses are forming as this is flowing down slope in these very steep parts here. Yeah, and you get the sense of the topography of a couple of them, right? Like you can see how deep this particular crevasse is right there as I tilt the surface. So those crevasses can be pretty dangerous if you're climbing one of these glaciers, if you're mountaineering in a glacial area and you accidentally fall into one of those crevasses, you're not likely to survive. Glaciers can also leave behind marks on rocks as they move over them. So this here isn't ice, this is actually bedrock. And this bedrock has been polished and striations or lines have been left in it, sort of gouge marks. Claw marks as the glacier has moved. And so the fact that these claw marks occur in this general direction means that either the glacier was that way and dragged in this direction, or it was that way. But they do indicate the direction at which the glacier moved. And my guess would be that it probably came off of these higher mountains over here. So the glacier probably flowed this way and then eventually receded back towards those mountains. You can also tell looking at this image and the way that the light is reflecting off different parts of the rock, that it's probably a pretty shiny rock, and that's because it has been polished by the motion of that glacier going past. Glaciers, as they move, are going to drag with them lots of sediment. They can hold it up because they're solid. So they can pick up everything from sand, silt, clay, up to boulder-sized things. And if they drag those pieces of sediment along the bottom, which they often do, then they're going to drag it against the bedrock which they cross, and that's what leaves these gouge marks, these glacial striations. And sort of over time, the action of many of these particles moving past is what's going to leave behind the polish. So the glacier is rubbing over and over again, the same way that you might, I don't know, polish a piece of fine metal, because we all have, so many fine metal candelabras and things like that that we polish in our everyday lives today. Same idea, right? So these Roche Moutonées is how that's pronounced, are names of these small hills, 10, 20, 25, 30 feet in height maybe, that form as a glacier moves over a spot in the bedrock. And as it's moving over that spot and it's changing its direction, it actually exerts sort of this negative pressure on this rock face, and it plucks these boulders off of this rock face and then sort of leaves them behind in a pile under the glacier right in front of that. And so the net effect of this Roche Moutonées is that you have this shallow surface on the up ice side, the side where the ice is coming from, because this glacier is moving in this direction here. On the up ice side, you get this shallow slope, and then on the down ice side, you get this area where you have a lot of boulders plucked off of this irregular, steep cliff face. These are probably only 10 or 20 feet in height, so they're usually too small to see in Google Earth, but I'll show you a picture of one here in a moment. And we can use these Roche Moutonées, like this low one that we have here, with the cliff face there. And this one that we have here, the cliff face there and the boulder pile at the bottom, to figure out which way the ice was flowing. So the ice on this one must have been flowing in this direction, and the ice on this one must have been flowing in this direction. We don't see these in Tennessee because Tennessee has not recently been covered, or I don't think ever been covered by any sort of continental or mountain glaciers. Even the Smokies were not glaciated in the recent past and during the past glacial cycles for the last few million years. So you don't see these here, but if you go to Ireland or Scotland or Nova Scotia, maybe places in Maine, places like that, you might see some of these Roche Moutonées. This name in French means rock sheep because somebody evidently thought that these look like sheep somehow. I'm not really sure how, right? Fluffy head. It's a sheep. Cool. A major feature that we can use to determine whether an area has been glaciated are the shape of the valleys. Glacial valleys are U-shaped. River valleys, or those valleys that have been predominantly shaped by streams and rivers, are V-shaped. So let me show you what I mean, right? So this glacial valley has very steep sides, and then it's flat in the center, making much more of a U shape. Whereas if this were a river valley, it would be much more notched and sort of constant slope on every side, and then a notch filled by the stream. Along with that, sometimes you actually see these hanging valleys that are higher valleys that represent places where mountain glaciers used to feed into one another. So there used to be a small mountain glacier feeding into this much larger glacial valley, and all of this used to be filled with ice. You get these hanging valleys where the small glaciers would have fed into the larger glacier. So if we walk through the sort of steps of changing in between U and V-shaped valleys, then we can look at this picture here. And so before glaciation, or when you don't have glaciers, a place like the Smokies, you're going to have mountain rivers, mountain streams cutting these V-shaped valleys. Pretty much the same slope on each side. It doesn't really flatten out very much in the middle. Very slightly flattened out, but for the most part, they're going to be V-shaped valleys. I'll show you a picture of what I mean here. So here we are in Google Earth above the Great Smokies. And if we tilt this landscape and we look at the shape that those valleys take, any valley that you pick is going to be V-shaped. So for example, this valley here doesn't really flatten out, but has a notch in the bottom. So that's a V-shaped valley, V-shaped valley, V-shaped valley. Everywhere you look, they're V-shaped valleys. So we could tell that the Great Smokies, at least recently, have been much more shaped by streams than they would have been by glaciers. And it turns out that the Great Smokies have not been glaciated. If over time the climate changes and it gets colder and we get some snow accumulation into these glaciers, then you would fill those same stream valleys with ice. Glaciers that are scooping along their sides as much as they're scooping along the bottom. And so the force of this ice is going to do lots of erosion all along the base and not just along the stream channel that had formed there before. And as a result, you end up, instead of having that V-shaped valley, you scoop away the sides of that V and you end up with a U-shaped valley. So that's why glaciers form U-shaped valleys, because they're scooping along the sides as well as on the bottom. Much like you have tributary streams feeding into a main stream, you can have tributary glaciers that feed into the main valley glacier. These valleys are not necessarily as deep as the valley floor here, so you might end up with hanging valleys once these glaciers retreat. You'll also have a system of, in these mountain glaciers, you'll have the highest points of the mountains themselves sticking out above the ice still. And these are a system of things called cirques, the bowl-shaped areas where the glaciers started. So those are cirques here. And we'll see more pictures of those. Arêtes are sort of the boundary areas between those glaciers, very jagged lines of peaks that separate one cirque from another. And then horns are where all of those arêtes meet up at the very highest point. So these arêtes all meet up right here. That's your horn. Again, we'll see pictures of those, but I wanted to show where they all are in one cartoon diagram here. Once the ice recedes after glaciation, the climate warms back up, the ice melts, and we see that in that area, we have that main U-shaped valley and a bunch of hanging valleys that now fill it. They're no longer filled with ice, so they can be filled with streams, and it produces waterfalls falling out of those hanging valleys, entering the main U-shaped valley. We see the cirques, the arêtes, and the horns labeled here. Over time, these streams might act enough on this area where these U-shaped valleys gradually turn into more V-shaped valleys. And that can happen over many thousands of years. Let's take a look at a U-shaped valley. So here we are, Google Earth. We're in sort of southeastern Alaska in an area that is still glaciated today. So we can zoom in and see one of those glaciers that are two of them meeting together into this further valley. And so if we tilt this, get a good look at some of the valleys that are here, we'll see that they have steep sides and then they flatten out in the bottom and they have steep side on the other side. That is what I mean by a U-shaped valley. You can turn all around and look at several of these. We see those U shapes in side profile, even where the glacier has receded from these areas. Clearly, this valley today is filled by a stream. And from here, it looks like it's probably a braided stream. But it hasn't had enough time since that glacier receded to really reshape this valley. And so as a result, it's still a very U-shaped valley with a flat bottom. Cirques are those heads of the glacial valley. Sometimes they're still filled with the remnants of a glacier today, like you see here, the very last dregs of a glacier filling the cirque still. And they sort of are shaped like a half of a bowl, right? Where the sides are very steep and the base is flat or hollowed out. And it sort of makes generally a semicircle shape behind it. So this is sort of like a half a bowl shape. And then if you go further down this way, you descend into a glacial U-shaped valley. So this looks like a cirque above a U-shaped valley that's hanging, a hanging valley over what's probably another U-shaped valley, but that's filled with water today. Here in Google Earth, I've flown us to the Tetons in Wyoming. And if we go up any of these glacial valleys here that are U-shaped, here's another example of those U-shaped valleys. You come to the end of any of those and you find a bowl-shaped depression. Some of them are filled with lakes today. Those are the remnants of cirques, the remnants of the glaciers, which we would call tarns, are the name of the lakes in the sort of uplands there. Some of them aren't really filled with anything, like this cirque here, or this cirque here, but all of those sort of semicircle shaped depressions with very steep walls that open up into glacial valleys would be called cirques. Here's another cirque, here's another cirque, etc., etc. Arêtes are the names of these sharp, jagged mountain crests that divide two areas that have been eroded by erosion, one on one side and one on the other. So this is probably a cirque down here, right? And there's probably another cirque over here. And the boundary between them, where the ice was starting here and it was starting here, and was sort of scooping away at the sides here and scooping away at the sides here, leaving this very jagged set of peaks here. Those jagged peaks separating these areas are called arêtes. So let me clean this up for you. In red here, I've outlined the whole system of arêtes in this area so that you can clearly see where those are. And then at the very peak is what we would call the horn. So this here, what this is actually pointing to, that's the horn, which is the terminus of all the arêtes and the highest spot. Let's take a look at one. Once again, here we are back in the Tetons. And the very jagged sets of peaks here that separate all of these glacial valleys from one another, very jagged peaks, all of those would be called arêtes. Not easy to hike up or hike across. Horns are where all of those arêtes meet up. So looks like this one, it's probably the confluence of 3 different sets of arêtes that all meet up at the very jagged, triangular-ish shaped peak. And this is what's known as the Matterhorn in Switzerland, very famous mountain. It's very steep. Mountaineers love to go try to climb it. This was created by glacial action because all of the areas around it have been scooped by those glaciers. And clearly it's mountain glaciers that have been doing the scooping here. One more time back to Yellowstone. Most of the named peaks here could be considered horns. So Grand Teton, certainly right here, could be considered a horn because it's at the meeting point of several different arêtes. The other Tetons, Middle and South Teton, could also be considered to be horns. Fjords are a special type of U-shaped valley that have been occupied by an arm of the sea. That is to say that sea level has risen and filled these U-shaped valleys. Still a steep side, flat bottom, steep side, but because sea level has risen and filled this area, we call it a fjord. You see lots of these in coastal areas in places like Norway and Sweden, but you can also see them in Scotland and Ireland and in places in Canada as well. Here I am on the northern coast of Norway, in a place aptly named Fjordgard. I'm going to turn us around and look up this valley so that you can tell that it is indeed a U-shaped valley, steep sides, flat bottom, that's been filled by an arm of the sea. If we come out here, we see that it opens up out into the sea here. We can see a whole system of fjords in the nearby area if we zoom out a little bit. Fjord here, there's a bigger fjord over here. And there's many, many fjords that fill this whole area where those glacial valleys have been filled by new arms of the sea. Fjords occur because sea level was lower during the LGM, that is last glacial maximum. So the last time that the glaciers were at their maximum extent, sea level was much lower. Why is that? Because the water that used to be in the ocean is locked up in these ice sheets. So here's an example of how far that ice sheet would have extended. And as a result, sea level is much lower. It was low enough that England, southern England, was connected directly by land to northern France. There's this whole area that's a treasure trove of archaeologists called Doggerland that's now off of the Belgian and German coasts that also used to be above water because most of that water was locked into these continental ice sheets. As that sea level rose, it was able to flood those U-shaped valleys and form the fjords. And so you get a whole lot of fjords in this area, and a ton of them on the northern coast of Norway. Related to fjords, but not exactly identical, are these things called drowned river valleys. So in other places, like this is the coast of North Carolina, the Outer Banks are here, and you have this system of drowned river valleys that I'm outlining now. Those were not glacial valleys. They were V-shaped valleys formed by streams, but they were around, near, slightly above what sea level used to be, but they've been drowned since sea level rose. Several other features include drumlins, kettles, and eskers. Drumlins are mounds of sediment shaped by passing ice. Kettles are depressions, often lakes, and if so, we'll call them kettle lakes, where blocks of ice sat on the surface and which later melted and produced these depressions that are called kettles. Eskers are serpentine, sort of snake-shaped sediment piles, like this one here, which formed because on the surface of the glaciers as they melted, they formed streams on their surface, and those streams carried sediment. And when the glacier melted away and left all that sediment behind, it sort of left these fossilized river deposits, stream deposits that used to be on the surface of the glacier, but were then just dumped behind here. So let's take a look at a few of those. So here we are above a farm field in Wisconsin, and if we tilt this view, we'll see that the whole surface is pockmarked in these sort of low mounds, some of which point in a particular direction. We'll see if I can find one that's got a good point to it. This would be a good example over here. Hard to see from just Google Earth, but we can see that this mound is elongated in this direction. It's a little stubbier in that direction. It's pointing in the direction of motion of the ice in this location. And it forms sort of a teardrop shaped, and it's just a little bit, and it's sort of elongated to the south here. And that's because the ice was moving to the south and stretched that drumlin out in that direction. So here we are above Minnesota, and we can see a whole bunch of these little lakes just dotted everywhere. A lot of these are going to be kettle lakes, formed where the ice, as it recedes from a continental glacier, left behind big blocks of ice that depressed the surface, that prevented any sediment from being deposited underneath them. And then when those ice blocks finally melted away, left behind these depressions, which later got filled with water. So Minnesota is known as the land of 10,000 lakes, largely because of these kettle lake depressions that were left by the last continental glacier. They're all over the place. Anywhere you look, it's going to be covered by these tiny little lakes and ponds. Some of them aren't really filled with water, or at least aren't always, like these smaller ones over here. These would still be considered kettles because they're depressions formed by the same process. Lastly, here's a good example of an esker that formed where the glacier had a stream on its surface that had this shape, and that had sediment deposits in it that made roughly that shape. And then the glacier melted out from underneath those sediments and left those sediments on top of the surface. We follow it carefully, we might be able to follow that same esker for a long ways across the map. But we'd probably want to be there in person to be able to track it, because these things aren't particularly high, 10, 20, 30 feet at most, maybe. So there are two features that we see sometimes. Both are depositional, right, sediment left behind, features of continental glaciers. We can separate Kames and Drumlins. Kames are places where you just had a hole in the ice that got filled with some sediment. It's kind of the opposite of one of those kettles. And those areas, those holes in the ice got filled with a little sediment, and the ice melted away and left behind that sediment pile. But it wasn't so much scooped by the ice itself. Whereas drumlins are areas where on top maybe of a bedrock outcrop protrusion, as the ice moved, it left behind these teardrop-shaped deposits on this ice. So the ice has to slow down just a little bit as it crosses this bedrock protrusion, and that leaves behind a lot of this glacial till, which is a big mixed sediment, very, very poorly sorted on top of that. And it is shaped as if it had been scooped in that direction. It's actually been scooped from this side, and the ice has flowed this way, leaving this teardrop-shaped trail moving off in the direction of ice flow. It's similar to current ripples in stream deposition, but the shape is opposite those. So in current ripples, the shallow side is in the upcurrent direction, but in drumlins, the steep side is actually in the upcurrent direction. Here are a couple pictures of those. Kames are roughly symmetrical because they weren't shaped by the ice scooping, filled with sand, gravel, till, whereas drumlins, till often underlain by bedrock, they're asymmetrical and they point down flow. So flow was that way because they've been shaped by the scooping of the glacier. Both of these are for continental glaciers, as are kettle lakes and eskers. A note on the Great Lakes, because these are a special feature of the most recent ice sheet. So it was receding about 14,000 years ago. And in these basins, as the ice sheet retreated, those basins, those low-lying areas were partially pre-existing, and they were partially scoured by the ice sheet as they went past. And they left the depressions that the Great Lakes have filled today. But those 5 Great Lakes, huge lakes, are actually remnants of where the ice had scooped and left behind these depressions. Types of sediment that you might get left behind by a glacier include till, which is very poorly sorted. So there's a mix of sand and silt in here, up to person-sized boulders. And they can all get moved by the glacier because although the glacier is moving slowly, it can pick up pretty much anything because it's solid. Water can't really pick up boulders this size unless they're moving very fast, but ice can. So it's a little bit of an exception to the rule that we have about the speed and energy governing the size of particles. Also, these tend to be relatively angular pieces because they weren't shaped by water in the same way. They weren't weathered away at their edges over time. So you'll often have angular to subangular clasts in this glacial till. Sometimes they get reworked by later stream action and they become more rounded, but they at least start out angular to subangular. In contrast, there's another type of sediment that is either pronounced lus or lurs, not loess. And this sediment is well-sorted, silt-to-fine sand. It's blown around. It sort of comes from glaciers pulverizing rocks into flour, leaving that sediment behind, and then that sediment can be blown away and deposited by wind. We care about it a lot because it makes very fertile soils. Because that powdered rock has a lot of nutrients that plants can dive in and get because the rock has been pulverized and broken down without being extensively chemically weathered yet. And so if we look at a map of where this loess is, it's in a lot of areas that contribute to farmland in the US today, sort of covering big parts of the Midwest, all the way from North Dakota, Colorado, Kansas, Nebraska, all the way east to parts of Indiana, Ohio, Kentucky, even part of Western Tennessee. And actually some of the thickest deposits are there on the edge of Western Tennessee. Here's a picture of some of the glacial till has covered this landscape, left behind some symmetrical shaped kames, and then some holes in the ground surface, which would be kettles, some of which are filled with water and are called kettle lakes. I want to mention what moraines are. So any type of glacier can leave moraines. Mountain glaciers leave a couple of special types. What moraines are piles of sediment left at the edge of a glacier. They're deposited there because as, say, a mountain glacier like this is moving down slope, it's picking up sediment, it's transporting that. And then where the glacier stops, sort of like a conveyor belt, it's spitting all of that sediment out into piles. And then if it sits in one spot for a while, it will build up a really big pile of sediment. And then it might recede some and then dump another pile, and it might recede some and then dump another pile. And so oftentimes, coming out of a mountain glacier, you'll see a system of these recessional moraines left behind when a glacier recedes. They're only left behind when a glacier recedes because if the glacier grows and passes one of its moraines, it's just going to pick up all that material and dump it further down slope. So it destroys those moraines until it starts to recede finally. The very final recessional moraine, the last one that you can find, is called the terminal moraine, and it represents the farthest the glacier made it. It's just a type of recessional moraine. And then these lateral moraines are left along the sides of the glacier. Lateral meaning sides. So in this picture of this U-shaped valley here, and this glacier that has receded, it left behind this pile of sediment here, which would be a lateral moraine along its side. And then it also left behind a system of recessional moraines. Here's one here. So at some point, the glacier sat in this spot for a while and dumped this sediment. And then this might be another one here, two piles nearby each other, but they both run across that glacial valley, and any other recessional moraines are going to be like that, whereas the lateral moraines run up the sides of the valley. So here we have a mountain glacial valley, and it's going to be tricky to see this recessional moraine here, especially from this elevation. It's much easier to see when you're down in person, and you can find those deposits of glacial till. That's what those moraines are going to be made out of. But in this depression here, we see this low mound of sediment that's sticking up over the top of that lake. And that is going to be one of the recessional moraines of this glacier. As it receded back from this point, it left behind that moraine. We might be able to make out a couple more if we get on slope, but they're probably at this point too well hidden by vegetation to really see any. This is really the only one that I can see from up here. Mountain glaciers leave recessional moraines. Continental glaciers also leave recessional moraines. And the very furthest ones, the terminal moraines, actually make up major features on our east coast. So some of Long Island is bedrock, but a lot of it is built up and was one of these terminal moraines. That is, the last ice sheet, the furthest that it got south was to this area, and left behind part of Long Island and Martha's Vineyard in Nantucket as just piles of sediment as it moved sort of like a conveyor belt, dumping it in that spot for a long time. Behind that is another recessional moraine, which makes up part of Cape Cod. And then you can find other moraines as you go further to the north that were also recessional moraines. So the sequence in which these things would have happened would, the glacier grew to about this spot, dumped the first set of moraines, Long Island, Martha's Vineyard, Nantucket, then receded backward, and then stopped in this spot for a while, dumping another one on Long Island, and then dumping out most of what became Cape Cod on a different recessional moraine, then receded to another level right about here, receded again, and so on and so forth, melting in stages, and as it receded, leaving behind these recessional moraines, the very furthest of which is called the terminal moraine. So there's this table that you might consider looking at that separates for you what some of these are. End moraine is another name for recessional moraine. And we talked about those. We talked about terminal moraines, which are a special case of those. Lateral moraines, which occur along the side of the glaciers. Where two glaciers join together would be called a medial moraine, sort of a lateral moraine that ends up in the middle of a new glacier where two smaller glaciers feed into one another. And then ground moraine is just sort of the name of the thin and patchy blanket of till left below the glacier as it recedes, not on a big pile. If we switch gears here just a little bit and talk about where the cryosphere is today, there is a big ice sheet that covers Greenland. But for the most part, ice is not permanent on Earth's surface. Most of the areas, even in the Arctic around that, there's some sea ice. But then there's also this feature called permafrost, which is soil whose water is permanently or discontinuously frozen, depending on how far north you are. So in this area in blue, the soil is permanently frozen. The water in it is blocked as ice, but it's not covered in a thick blanket of ice. It's incorporated into the soil. And then in green here is discontinuous permafrost. During part of the year, that soil water will be frozen. Or it's sort of, in other areas, it might be patchy, where that permafrost is actually frozen year round, but only in, patches here, et cetera, et cetera. In other places on high mountains that are still farther north in latitude than some other things, you'll have mountains that have some permafrost at the top of them as well, permanently frozen. Let's talk a little bit about glacial cycles and climate change. So very briefly, about 18,000 years ago, the northern hemisphere continental glacier was at its furthest extent. And we can tell that by things like where the terminal moraine is located. You can also tell that by reading data from ice cores that still exist in continental glaciers and figuring out the temperature was lowest at about 18,000 years ago. So this is about as far as the ice ever got. Descended pretty far in the Mississippi River Valley, right? So the Great Lakes would be somewhere about there today. And Long Island would be in there, Cape Cod would be in there. It did not reach nearly as far down as Tennessee-ish. But you'll also notice by looking at the way that the coastline looks, that the sea level was lower, right? Florida today is more shaped like that. And the continental shelf around it was actually exposed at the surface because so much ice was locked up in that glacier. We'll talk in a future lecture about why it was that Earth's surface was so much colder 18,000 years ago, and how some of those natural changes are related to artificial anthropogenic changes going on today. Further in Earth's past, so in the Pennsylvanian Permian, so this is the Paleozoic, right, before the age of dinosaurs here, there was another glaciation on the supercontinent that consisted of South America, India, part of Africa, Australia, Antarctica. And so there was another continental glacier that spread out there. That ice is not the same ice as is on Antarctica today because Antarctica melted in between, and it's only been since maybe 45 million years ago that Antarctica has been covered in ice. But this particular ancient continental glacier, we can see evidence of today, covering parts of South America, Africa, and India. Clearly, there's no ice covering most of India and central southern subequatorial Africa today, or Australia. This is a huge desert here, actually. But we can see evidence of those glaciers in the rock record. We can find fossilized areas with glacial striations and glacial polish, buried under many more sets of sediment, right? Glacial till left on top of it. That's been fossilized and turned into a new rock there. But these ancient tills are evidence that there was a continental glacier that covered large parts of the southern hemisphere at that time. We can also find these sediments that are like these lake sediments, very fine grained sediments deposited in very still water with these large boulders just plopped right in the middle of them in certain spots. These are called drop stones. These are also good evidence that there was a glacier nearby. What happened was an ice raft floated out onto this lake, and that ice raft contained this boulder. And as the ice melted, it dumped that boulder in a spot on the lake. So drop stones are just stones dropped by, think of icebergs essentially, that are carrying some rocks in them and then drop them as they melt.